Welcome, recruits, to Phase 1 of Get Your FRQ On. AP Calculus Bootcamp. Your clearance has been verified. Today's operation focuses on limits and analytical procedures, covering topics 1.1 through 1.9 of the course and exam description, or CED. This intelligence accounts for 10 to 12% of your AP exam, so pay attention. Let's begin. Here is your situation report. In the past, you relied on standard algebra, static intel. Algebra allows us to calculate an average rate of change, but it requires two separate points and completely fails when the time elapsed is 0. Calculus gives us dynamic intel. It allows us to calculate an instantaneous rate of change measured at a single, exact moment. Our primary objective today is to bridge the gap between static algebra and dynamic motion, and the weapon we use to do that is called the limit. Let's break down the target identification and standard notation. When you see this expression, you need to recognize its three components. First, the approach. This tells us the agent, x, is moving arbitrarily close to c. Crucially, x does not ever equal c. Second, the path. This is the function, f of x, that you are navigating. And finally, the target L, which is the intended destination y value. Warning, the limit describes the journey, not the arrival. The actual physical location of the point is irrelevant to the limit. We begin our visual reconnaissance by flanking the target graphically. For a limit to exist, you must execute a coordinated approach. You will approach the target x value from the left flank and simultaneously approach from the right flank. The success condition for this operation is simple. The left flank height must exactly equal the right flank height. Note that encountering a hole, or discontinuity, does not stop the limit from existing as long as both flanks are targeting the same coordinate. Next is data interception via numerical trends. When standard visual intel isn't enough, we scan the data tables. Here, we observe the input values approaching our target of 3 from both the lower end and the higher end. The protocol requires you to scan the trend in the output values. Because the outputs are converging on a single number from both sides, we can estimate our target limit as 5. Listen up, because these are your standard operating procedures. Your primary directive is always direct substitution, which should always work for a continuous function. Step 1. Plug your c value directly into the function. Step 2. If the result is a real number, mission complete. Step 3. If the result is undefined, your function is not continuous, and you must engage secondary protocols. Remember your operational limits. The limit of a sum is the sum of the limits, the limit of a product is the product of the limits, and the limit of a constant is just that constant itself. Be on high alert for our primary threat level, the indeterminate form. If direct substitution yields 0 divided by 0, do not panic. This does not mean the function is undefined, and it does not mean the limit does not exist. This code simply means more work is needed. You have detected a hole in the graph, and specialized breaching tools are required to proceed. When you hit 0 over 0, you must deploy countermeasures. Tool number 1 is factoring. Use this for polynomials to factor the numerator and denominator. Then cancel the common term to remove the hole. Tool number 2 is conjugates. Use this for radicals by multiplying by the conjugate to clear the root and reveal the cancellation. Tool number 3 is trig identities. Swap out expressions like tangent or sine squared for equivalent forms to simplify the function. If none of these work, you will need to connect with Commander L'Hôpital. Commit this tactical decision protocol flowchart to memory. Start with direct substitution. If the result is a real number, mission complete. If you get 0 over 0, it's an indeterminate form, so you deploy your algebraic countermeasures. But if you substitute and get a non-zero number divided by 0, you have hit a vertical asymptote. In this scenario, you must investigate the signs to determine if the function is approaching positive or negative infinity. For highly specific threat scenarios, we call in special ops the squeeze theorem. We refer to this as the pincer maneuver. If your target function, f of x, is trapped between a lower function g of x and an upper function h of x, and the limits of those outer functions are equal at the target point, then f of x is forced to the exact same limit. The target has nowhere else to go at the pinch point. Total situational awareness requires fluency in 3 languages: numerical tables, visual graphs, and analytic equations. A successful agent can seamlessly translate between these. If you see a graph, you must be able to write the notation. If you see a table, you must be able to sketch the trend. If you are given an equation, you must be able to verify it with table data. Time for the after-action report. Let's debrief. 1. Limits predict the destination, even if the bridge is out. 2. The left flank must equal the right flank for a limit to exist. 3. 0 over 0 is simply an invitation to deploy algebra. 4. Always verify your hypotheses before executing theorems like the Squeeze theorem. You are now prepped for the next phase, continuity protocols. Status: dismissed. For more AP Calculus worked out free response question solutions, like and subscribe to get your FRQ on.